The following is an excerpt from the book Experiences of Thought by Anthony Kahn, available now on Amazon.com and Kindle. Lucrative Logic in Matters of Matter, A Quantum of Solace. General relativity has been the most successful model to date for predicting the behavior of our universe on the largest of scales, where the force of gravity dominates. But we must resort to a different paradigm when we consider the universe in close-up. If we examine all of the forces that are at work in the dynamic universe as a whole, we can categorize them into just four principal fundamental forces. These are the strong nuclear force, weak nuclear force, electromagnetic force, and gravitational force. The strong nuclear force is, rather logically, very strong, but drops off very quickly with distance. It binds the nuclei of atoms together, despite the mutual repulsion of their component subatomic particles. The weak nuclear force is the key force at work in radioactive decay and plays an important role in nuclear reactions. The electromagnetic force is probably that which we have the most experience with in everyday life, as it gives matter its solidness and is the reason you experience such phenomena as friction, magnetism, and elasticity. It is also why you don't fall through the floor in the presence of gravity. Lastly, gravity is the longest-reaching but weakest of the forces, and is the force that anchors us to the ground and keeps the moon in orbit. Now, the holy grail of physics is to neatly explain the behavior of these four forces in one all-encompassing model, a grand, unified theory. But the best we can do at the moment is to tie the first three into a single model, the standard model of particle physics, and then use general relativity to understand gravity. The standard model is our way of conceptualizing the building blocks of matter and understanding how they interact with each other. The idea of microscopic, indivisible particles constituting the matter we experience in everyday life is nothing new and was already on the minds of ancient Greeks such as Democritus. As it turns out, however, as you might expect by now, the universe once again does not act on these scales in the way we would intuitively expect, as we shall see. The way the universe functions on the smallest of scales really is bizarre, and scientists are still trying to make sense of it all. Nevertheless, the standard model affords us some small solace in our endeavor to come to grips with its behavior. Quantum is the new buzzword you hear all over the place these days. If a company wishes to sound technologically advanced, it throws the word quantum around. But what does quantum mean? Nothing fancy, actually. It simply means a discrete unit of something. So, in contrast to the idea of a continuous spectrum of possibility, quanta are discrete, allowable values, where any values that might have lain in between are disallowed. We can liken quanta to the children's building blocks that we discussed in section 3.2. Just as children so often learn the basics of numbers with these discrete, whole building blocks and come to understand numbers in terms of integers, it turns out that nature, at a very deep level, is rather fond of discrete integers too, favoring specific allowable values rather than a continuous spectrum. One of the earliest clues to the prevalence of quanta in nature came in the form of light spectra, the good old rainbow. If you can examine the spectrum of the sun at very high resolution, you will see distinct lines in there, corresponding to very specific colors. But why are they there? It came to be understood early in the 20th century that electrons cannot exist just anywhere around the nucleus of an atom, but rather there are specific energies they can possess, corresponding to allowable energy levels or orbitals. Furthermore, the electrons can jump between energy levels by absorbing and emitting photons at specific energies. The energy held by a photon is inversely proportional to its wavelength, which we interpret as the sensation of color when the photon is absorbed by the retina in our eyes. Of course, all matter that we are familiar with is formed from such atoms, and if we use prisms or gratings to spread the light emitted or reflected by an object into its component colors, we find that there are specific wavelengths, i.e. colors, that are either much brighter or almost absent. These wavelengths correspond to the energy differences between electron orbitals within the constituent atoms of the object. Sometimes foreground atoms will absorb a specific wavelength, leaving a dark line in the spectrum. Other times, electrons will cascade down through the allowed energy levels, emitting photons that produce bright lines in the spectrum. Spectral lines are actually how we can tell what stars are made of, and much more besides, because they are the signature of specific atoms in specific states. You might have noticed that when we discuss photons, we tend to be referring to them as though they are little balls of energy. But isn't light made up of waves? How else can it have a wavelength? Well, this is where things start to get interesting. Actually, light can be thought of as both a wave and a particle. How we might choose to envisage light generally depends on the scenario. But it is not just light that exhibits both wave-like and particle-like behavior. It turns out that all subatomic particles exhibit this dual nature, including those that we are made of. This brings us to discuss one of the most famously bizarre observations in all of experimental physics: the dual outcomes of the double-slit experiment. Have you ever watched the interactions between water waves in the ocean? You will have probably noticed the emergence of some interesting wave patterns where portions of different waves collide with each other. If you have two vibrating bodies in a pool of water, they will emit ring-like waves that overlap with each other, and the resulting wave crests will either be larger or smaller, depending on the position. This is a process called interference, and it is a natural property of all waves, including light waves. If we set up a coherent source of light to shine on a screen after first passing through two slits, we get an interference pattern. The light waves spread out and pass through the two slits, which act like their own point sources, producing wavefronts that overlap with each other. But something very odd happens if we attempt to track the path of the individual photons being emitted from the light source. If we can set up our experiment so as to observe which slit they actually pass through, the interference pattern disappears. Rather than observing an interference pattern on the screen, we now simply see two blobs of light where the photons from each slit land. Somehow nature knew that we were monitoring the individual photons. Consequently, the light ceases to behave as waves and instead takes the form of particles. Why is nature playing tricks on us in this way? This result betrays so much about the mechanics of the universe and lies at the heart of the formulation of the Standard Model. You see, choosing to speak of light as waves or particles is really more than just a question of convenience. It comes down to how we look at it. Light takes on the form of a wave unless an observer measures properties of the individual photons. So in other words, a photon of light doesn't actually have any fixed position until an observation is made. It just exists in a cloud of possible positions described by a wave function. It's self-governed by an equation formulated by famed quantum guru Erwin Schrödinger. In the Standard Model, the various elementary particles are described in terms of a set of quantum numbers. These numbers take values from sets of discrete integers or fractions thereof, and together describe every possible state of the particle. Each particle can thus be thought of as existing in the form of a distribution of parameter values, with some parameter values more likely to be measured than others. Even electrons don't really behave like miniature planets orbiting the atomic nucleus, but likewise take the form of clouds of probability. It is not until we take a measurement that the particle presents itself as having a particular value for the measured parameter. So in the case of the photons of light in the double-slit experiment, the positions of the photons are drawn from a probability distribution comprising all allowed positions upon the observer measuring them. Otherwise, they occupy a range of positions and can pass through both slits in the form of a wave. There are some additional peculiarities that arise within the realm of the quantum world, and we will not discuss all of them here, but there are a few we should briefly mention. Firstly, there are limitations on how accurately we can pin various paired properties of a particle down, as famously embodied in Werner Heisenberg's uncertainty principle. For instance, the more accurately you pin down a particle's position, the less accurately you can know its momentum. Secondly, if we are describing particles' positions in terms of spread-out probability distributions, they can turn up in some interesting places, including the other side of hard barriers. This phenomenon is known as quantum tunneling. Thirdly, sometimes it is impossible to describe a particle without reference to another particle, leading to a phenomenon called entanglement. The particles in this situation have to be treated as a single quantum system, and correlations can exist between certain properties of the constituent particles, meaning that you can know certain properties of one entangled particle by measuring another particle in the entangled system. Given the weirdness of the behavior of particles at atomic scales, why is the macroscopic world we inhabit apparently free of all these paradoxical goings-on? A lot of it seems to come down to the decoherence that arises as we add more and more quantum systems together. Whenever you add two waveforms together, you will get interference. But the form of the interference pattern depends on the individual interfering waves. If you have two waves that share the same shape and the same frequency, then when they interfere, the resulting pattern will have special attributes, and properties of the original waveforms will be preserved. This kind of interference is said to be coherent. The problem is that to accumulate enough matter together so that we can actually see it with our own eyes, you have to throw together trillions and trillions of particles, i.e. waveforms, and any coherence is lost. You will just end up with an averaged out mush that behaves in the predictable ways that we are used to. Under certain circumstances, scientists have been able to bring quantum effects to macroscale quantities of matter and observe some very interesting and useful properties, but in everyday life, the weirdness of quantum mechanics is washed out. All in all, quantum mechanics is a mind-bending state of affairs, but it has been shown to fully account for the humdrum, classical observations of the macroscopic world, as well as the bizarre goings-on of the truly microscopic world. It scales very nicely in this regard. It just falls over with that fourth fundamental force, gravity. Despite its success at predicting all manner of observations, it can, however, be very difficult to truly understand what is going on outside of the mathematical equations that define it. There are actually a range of standard interpretations of what it all means, and they can disagree on important points. The many worlds theory, for instance, which provides inspiration for many a sci-fi film, is actually one such interpretation. It posits the existence of many universes in order to account for the seeming randomness that quantum mechanics demands. Every outcome should occur in some universe, or else there cannot really have been any probability of it occurring at all in the truest sense. This is in contrast to the more popular Copenhagen interpretation adopted in this section, which finds no such need for each possible scenario to play out. Within its reckoning, a quantum system instead exists in all possible states simultaneously, requiring the existence of an observer to initiate wave function collapse. There are nevertheless differences of opinion as to what precisely causes the wave function collapse into an observed quantity. It would seem that an observer is necessary, but what actually constitutes an observer, and what role does an observer play in the process, if any at all? At the end of the day, the Standard Model and its underlying quantum mechanical interpretation of matter and energy has been a great boon to understanding our world at a very deep level. But, like general relativity, it cannot be called a complete model and leaves a number of important questions open to debate.